You could all introduce yourselves, but there's no need for that. Nobody else wore a tie, so I have to give the presentation today. I thought Charlie was going to bring the donut holes.
They're out on that side.
They're out there in the kitchen area for us, huh?
You didn't see the bagels out there?
That's it. I should stuff a bagel in my mouth and start talking, right? Let's see. Give us a nice wireless mouse. Does everybody want to play with it? All of you know how to use a Trace32 emulator already, but you'd all like to use it better. You'd like to learn new things you can do with it. And the Lauterbach emulators, Paul picked them out many years ago because they were the best in the industry, and we still like them a lot. They do everything we need to do. They do almost everything they need to do in the OS group too. They use them a lot heavier than we do, and actually they're the experts in it. When there's things you need to do and you can't figure out how to do it, you might wind up talking to them. But we're going to go through stuff that we have. You're all familiar with it. Everyone here knows the 80 assembly language. Some of you know how to do C language programming. All of us are going to start using more and more C language programming in the near term, really. So I'm going to talk a little bit about that. I assume you've all got familiarity with the Lauterbach Trace32 emulator. You know what the windows are. You know how to start and stop it. You know how to set breakpoints. So I'm not going to try and teach that part. To teach that, I should have brought an emulator in and gone through all that stuff. But instead, I'm going to show slides. I'm going to talk about the various things. And you've all got these handouts now. There's 2 handouts that are stapled. I'm not going to show those handouts or really talk about them, except briefly right now. The one with the screenshot on the front is basics that you already know, how to get it started and things. It actually goes in and has instructions for entering an analyzer program, how to start it, how to stop it, how to set it up for triggering, all sorts of fancy things. And to learn how to do that, you really need to have hands-on. So here's some notes to help you learn how to do that. In the course, we're going to talk about some of the programs that you would key in when you actually want to do an analyzer program. The other handout is something that's needed for C programming. If you want to do source level debugging, if you code in C, looking at the disassembled code, all that assembly language and all that, you get a whole bunch of assembly language for each C instruction. It certainly doesn't work at all there to do that. So you have to use source level debugging when you work in C. And it turns out that source level debugging also works in assembly. So the new people are starting to do source level debugging in assembly. I recommend that if you have time, try it. You'll actually be able to see your assembly language the way you keyed it in rather than the way it disassembled it. When it disassembles it, it knows some of your tags, it doesn't know others. It makes it look kind of funny. If you look at the original, it looks a lot better. Well, I'm going to actually get to that a little bit later, but that's what these other 2 handouts are. I'm going to go through the slides. And now that you know what I'm assuming, we're going to start with basic things, some of which you already know. We're going to go into some of the parts that you work with when you say do space emu conf. That's executing a script file. Let's take a look at that script file. It's not scary. We can go into the parts of that. And after we've gone over the basics, we're going to talk about the advanced usage, the trigger unit, the analyzer, those things, and some of the programs you can set up there, some of the fancy type information you can gain with that. Under the basics, we're going to talk about the basic commands that you go through. The script internals, that's the the CMM files, the internals for those, and source level debugging. We're going to talk a little bit on that to help get you into that other handout. When we start up the emulator, we do a do space emu conf and a do load. When you start up the ROMulator, see, I'm pretty quick, aren't I? When we start up the ROMulator, we do a ROMconf and a ROM load. Actually, those names, those of you who have used ROMulators, maybe those aren't the exact names. You can name the CMM file anything you want. I collected a set of ICE ROMulator files together, and I put them in G, development tools. Oh, I'm supposed to point up here, aren't I? Current ROMulator, that directory. So anybody who's doing debug with a ROMulator, you can get the full set there. There's a readme.txt there that tells you how to set these up and how to use them. Has everybody here read the Lauterbach Trace32 books? These 4 nice books that are translated from German and so easy to read. Perhaps not everybody here has actually read them, huh? There's one of these. This one has the practice user's guide and practice reference. Practice is the name of the script language that Lauterbach uses for their CMM files. So we're used to this word practice that sounds like we're playing or we're over learning how to do something. Practice is a proper noun to them. That's why it's all in caps on this slide here. It talks, this practice script language is what the CMM files are written in, and actually these manuals are pretty easy to read if you get to the right manual and you understand a few key points. There's lots of manuals that aren't easy to read though, so you don't have to try and read them all. But the practice script language is what emuconf, Gitboard, map memory are written in. So let's look at some of those. Let's see. Well, we're not looking at them yet. I just talked about this slide, didn't I? Practice is a line-oriented test language which can be used to solve all usual problems of digital measurement engineering. I got that quote directly out of the practice user's guide. See? It's written in English. We can understand it. Some of the program elements in practice are labels begin in the first column, and we'll look at some CMM files so you can see this. Labels begin in the first column. They can be followed by an optional colon. They don't have to have a colon on them. Commands are indented with at least one blank space. They can be on the same line as the label, or they can be on a different line. And there's only one command per line, so we can't put multiple commands on a line. It's not quite freeform like C. Comments are prefaced by a semicolon, and the semicolon must be located at the beginning of a line. So you cannot have comments on the same line as any commands, obviously. Some of the instructions, the commands that we can use in the practice language, we can use a stop instruction, an end instruction, continue. Do is how we call a program module, and inside the program modules, if we want to call another one, we use a do. End-do terminates that program module. That's the end of our routine, whatever. It's how we return back to where we came from. Go sub, you would be calling a routine that's in the same CMM file that you're currently executing. Return, what this do executes a CMM file actually. And that CMM file could have several routines in it. The return is how we return from a subroutine. If you're inside of a module, you do a go to. If you want to jump to another module, you do a jump to. You've all learned more than one programming language, and this is a simple script language to help us get around and do these things. I'm not expecting anybody to write new scripts, but the scripts we're going to look at are the ones that we're using every day, so familiarity with them and an ability to make minor changes to them is sometimes useful. We can have conditional code, if and else. We can have a loop and a while, a repeat. We can look for an event to occur. We can wait for an event or delay time. We can use parentheses to mark a block of commands. So if you have an if, you'd have an open parenthesis to mark the extent of that conditional. If you had a block of commands, like right here, that this is a separate command, so it goes on a line of its own. This is another one. You can, these have to be indented at least one space. If you indent them several spaces, it reads easier. And it's probably best that we all use C-style formatting, since some of us use C and all of us are going to. To have variables, they actually have something called macros, and the macros are used as variables. A macro begins with an ampersand, and it can contain arithmetic value, Boolean value, or a string. So it just, whenever, well, and they can be local or global. Local means they're just in the module you're in. Global means they're throughout this program that you're executing, even if it calls other modules. If we had a global variable, or local variable, we declare it first, and then we use it. We set it to a value. Later on, we can use that value. And in the scripts we have, we do use these macros, these variables. We can print information to the screen. We can make noise with the beeper. We can enter information. We can request information from the user in a window or command line environment. We can input a single character. And as far as screen goes, we can update the screen. We can tell it to update the screen every command line. We can update the screen on print commands, these things. Or we can turn the screen completely off so we can do a bunch of stuff and then later on tell it to update the screen. And like I said, I don't have the expertise to generate new code, but I can look at some of the scripts we already have, some of the CMM files, and modify them. And probably you'll be able to when we're finished as well. We can modify files on the disk. If you need to read or write files, you can open, close, read, and write them so we can save data. Okay, let's look at one of the files that are in here. This is the emuconf.cmm that I had in my directory. I was working with SmartIce. So this may be slightly different than one that you've got. This file is maintained by the OS group. They've got it under PVCS version management. That's why we see it's got our standard stuff up here. And Keith is the last one to check it in. It looks like he checked in the initial version for SmartIce. because that was a new project. He started a new set of it. As we know, EMU comp configures the emulator. Emulator configure. You can do EMU comp, or you could do EMU comp space FEM75 if you wanted. So you wouldn't have to wait till it asks the question of what board type do you have. Probably several of you didn't know that. I didn't know it until I read through it.
Wow.
Here's some more of this. I couldn't fit all this on one slide unless I made the print too tiny to read, so I split over 4 slides. We define a local macro or a local variable, and we ask for the board type. The E colon selects the emulator system. This is, it's got more comments in it than it has code. That's good. That makes it easy for me to tell you what it does. I can just read the comments to you. Reset, define a global variable to hold the board type, so it's global board. See, this one was a local variable. This one's a global variable. That means it is going to be available to the other functions we call. And board equals something here.
Force select.
Yeah, and that is a variable because it has an ampersand on it. I don't know where it came from. Oh, it's up
If
here.
you entered it when
Yeah.
you type in, and probably
That's right.
then when you hit 2.
That's the same one that's up here, isn't it? Define a global variable to hold the number of boot pages, and we started off defaulting to 1. The number of boot pages on SmartIce turns out to be 3 right now. So later on, one of the other CMM files we call will look to see, oh, look at, they're on a SmartIce, and it will change the number of boot pages, but we're starting it off as a 1. We're setting up some more variables here, global variables again, to hold the physical address and physical page number of the upper memory page. This is technical stuff that the OS people work with. As far as we're concerned, it's just the upper memory page, but with the hardware, the various kinds of hardware, they actually have to assign a page number to that in their way of talking. We clear windows. We do get board, which gets the board type. We're going to look at that in a minute. We do a win clear, clear the screen, disable all functions, it says, set the system to reset down. Here's the second module we call do map mem. Set up the memory mapping for whatever type of board we're using. We're calling another one do T32 win. The T32 win is located off in another directory completely. That's the way you've got your desktop set up, the arrangement of windows for it. And that first handout that we talked about that had a screenshot, that's the way Dick Malakovich has his desktop set up. His T32 win is different. Sometimes when you go move windows around, when you go to exit Trace32, it'll ask you, do you want to save your desktop? If you save it, it'll modify T32 win. And next time you'll still have those changes. We turn the functions back on. We tell it that there's that screen.always that we saw earlier. We're just going to change the update rate to 5 per second. And in do, we must be at the end of this CMM file. One of the CMM files they called was getboard.cmm. See this comment, this practice file checks to see if the global macro ampersand board is defined and counts for a new value if it is not, or if it's invalid. That's a confusing word to have in there, this practice file. That's why we learned earlier what practice meant. It looks like they'd given us some files to practice with, and somebody was too lazy to fix the comment, but that actually means something. we look to see what value does the board have coming in. Is it an FTP 70, 74, whatever all these things are. Here's the rest of them. 71. Did we have an FPM 75 in that list anywhere? Oh, yeah. If it's a 73, do that. And here's the 75. That's the one we're usually working with now on ice. So they got to have a big comment. That when we do things now, we add better comments than we used to. We've been using the Lauterbach emulators for about 5 years here at Hypercom. I probably should have pointed that out in the beginning. Before that, we had HP emulators, and at least one of you has used HP emulator, haven't you? You never used it? Okay. Nobody here has used an HP emulator. Jeff? Well, that's because you're here for the second time.
The first one.
Yeah. We probably still have a couple of those HP emulators lying around someplace. They were the original development tools we were using here. I've used one. They are not near as capable as the Lauterbach emulators. You can't do a single step with them. You can't single step through the code. And if you can't single step through the code, it's not very friendly. So single step is about all most of us use. Breakpoint and then walk through the code. We're going to learn to do a lot more today. But with those emulators, those HP emulators, you couldn't do that. So we came up with better ones. If it's a 75, we're setting the upper memory address to 070000, page 7. We're setting the upper memory page to 7. We're setting the number of boot pages to 4, because in Flash we can have up to 4 boot pages. And then we're finished with this get board. So we can look at, there's some more in get board. I don't know what it was. Oh, if it's not defined, then you've all seen this list thrown up. These are our choices, and we pick an 11 usually. Those of us who are working with Smart Ice now, we're picking a 10 because they don't have Flash in the Smart Ices yet, and we have to load the boot pages into RAM. If you have real boot in there, if you have Flash in there, then the boot pages are already there, and we don't have to load them. We pick an 11. When you pick 10, the load file is going to go figure out where the boot pages are and load them into memory. Didn't I push the button? There's 4. And if you select a 1, it sets to this and so on, and that goes back up to the start. That was probably back to the beginning of this, right here. And then we go through the process and we do the right stuff for the board. So this is where, if you've actually entered it already, if you do EMU-conf space FEM75, it won't prompt. But if it drops through because nothing's been defined yet, it'll set the board here and go on. The next thing the EMU-conf called after get board was map mem. And this is common type of commands it has to do. This is a tricky instruction here. We glued together, somebody glued together map mem underscore with the board type. This ampersand board is one of our macros, our macro variables. So this tricky practice language created a destination tag from that. If we're on FEM75, we didn't jump to any of these. All these don't have to do much. They do 2 lines. Let's go on looking further. If we're this type, here's the 74, 71, There we go. 71C, 73s. Here's our 75 that most of us are choosing right now. It calls some function called yeah, it looks like MMU term. Or MMU. Okay, it's two M's. System.bank file, fbm.bank. Let's look at this instruction. System.bank file. What does that mean? I don't know. But we've got, I brought these books here. The FET book has something in it called reference. And it probably tells us what a system.bank is. SYA. Symbol. System. System.bank file. The format is system.bank file and then a file name. Loads an extension for bank switched targets to the emulator control program. For details, check the emulator probe manual for your processor. The bank definition file must be a pure binary file. It can be generated by a data.save.binary command. Okay, well, it sounds like we really don't want to know any more about that anyway. But when you're looking through these CMM files, you want to look at the practice manual for the types of things we can do, like go to. And then it actually contains the same type instructions you can type in the bottom of your emulator window when you're typing things like setting breakpoints. You can type a system.bank file line. But since we don't really understand it, I don't think we should do that. And we map.ram. We could look up map in here as well. We do molmem, whatever that is, and then we undo, or MMU mem, MMUL, mmolrem. Here's MMU term. Oh yeah, now we're in the map. Can I go backwards? Weren't we already in map, ma'am?
We called it from the page above, and here's sort of describing what it is.
Okay, what one were we in before? Map, ma'am. Oh, I see.
Batman 75.
I'm not very good at changing these numbers up here in my slides. They're all page 1. Yep. Okay. Remember the print command that we had in the practice manual? We can print stuff. We're actually printing something. So we see we really do those things. Let's get on to some of the other stuff. The source code debugging, source level debugging. That means you get to see the code as you typed it. In order to do that with assembly or C, we have to observe certain things. But we can look at your source code. That disassembled machine code, it does a good job of figuring out what we must have put in our assembly code, but it doesn't do a perfect job. Works for C or assembly code. Come on now, I already said that. In that hit, did I tell you this yet? In G, development tools current, T32 source level debugging. No, I hadn't given you this yet. This directory here is where all these files are located that are on that second handout, the one that doesn't have the screenshot on it. If you want to set up source level debugging for assembly language, you go get the tools out of here. You read that handout, but this is where all those tools are located. Paul Walters, when he came here, he said, why aren't we using source level debugging with our assembly language? Because he's got experience with other emulators, and he tried to make it work. It didn't work. He talked to a fellow in Germany called Stefan Lauterbach. It turns out Lauterbach emulators or family name. He talked to Stefan, and Stefan gave him some fixes so that it would work with the assembly code. And that handout tells you the changes you need to make with that. Maybe we'll change built-ins to better support it so you don't have to change as much. But right now, that tells you everything you have to do. You copy these files down, you make a few minor changes, and then you're using it. But you got to read that handout first. Or let's go back there. That handout is the readme.txt that's in this directory. I thought you knew that. If you're doing source level debugging with C code, you'll wind up in your load file loading pages with something that looks like this: do space ld file space hs3 18./nb. Do load file is this is the CMM file you're calling. hs3 is the page that you're loading. In HDT, they've got an hs3 page. HDT is the CPOS or the Tejas project. All those various names we've got for the C code they generated in Texas, and that we're all starting to use more and more of. Page 18 decimal is the page they are loading. /NB means no automatic HLL, that's higher level language, breakpoint setting. There's not enough memory in our Lauterbach units. So if you don't do that, you'll get partway through and it'll run out of memory, unless you got a small program. The HDT is not a small program. And our normal application programs in assembly language probably aren't small enough either. If you want to set breakpoints on a range of your code, you can use break set HLL command. The way the Lauterbach emulator does single step mode with higher level language is it sets a breakpoint on each of your source lines. In assembly language, there's almost a one-to-one correspondence between the source lines and the machine code lines. So we're all used to walking through the code, and we didn't even realize there wasn't a one-to-one correspondence until we got to a macro, and all of a sudden we had to wade through a lot of code. In C, it's very clear. A line of C code generates a bunch of lines of machine code. And if you want to walk through that code one instruction at a time, then you need to set HLL breakpoints for the range of code that you're trying to walk through. Well, we are talking C. There's also an option /puzzled. Puzzled rearranges the C code to match the assembly language. Sometimes when the emulator is reading your source file, it gets lost, and this causes it to reorient itself often. So it's not lost, but it also causes it to mess up the indentation, and it's very hard to read your code at times. In Dallas, they normally do not use the /puzzled. Sometimes the C code doesn't line up at all with the rest. You get big blue spaces where it's not showing you any C code. It's color in there, the screens are in color, and it shows the disassembled assembly language in one color, the C code in another color. It's not showing you any C code. If you add the /puzzled when you load that part, then you can actually debug that part of the code as well. But we don't care about that yet. You'll care about it later, and you'll come back and look at these notes. I didn't mention, and in that handout that Paul Walters wrote for us, it talks about the, in fact, what happened to that?
You skipped one.
Well, I got the wrong slide set up here. I've got the old slide that just has one slide here for source level. No, it has that one. Where's the rest of my slides? There should have been more slides, right?
No, that's the next one.
Yep, there's this one that says HLL mode, mixed mode, single stepping. I don't seem to have that one here. Oh, there, I found it. I skipped over it earlier. That's how come. In the HLL mode, higher level language mode, you're viewing only your code, your C code, your assembly code, whatever. In mixed mode, you see a section that shows your code, and then the disassembled machine code is right underneath that. You get to see both of them. The mixed mode is the way that most of us would look at it because we're used to the assembly code. When you're looking at C, we'll probably eventually get to where we prefer HLL only. And this is where we talked about those breakpoints that I was talking about. Okay, good. The HLL mode, there's a little button down in the corner where you switch the modes, and you have to actually use it, so hopefully somebody will show you where that button is someday. I'm not going to show you. Okay. How are we doing on time? Oh, good. We're gonna get through this in great time, unless we slow down now. Did anybody fall asleep yet? I've got something tricky coming up here. I'm going to teach you about something, and then later on I'm going to ask you what the right choice is. There wasn't enough room on the slide to put that, so you better be paying attention. Lauterbach has another language. We know about the basic commands. They're all in this big fat reference manual. We've learned that there's another language called practice. Which is their script files, their CMM script files. They've got, for their analyzer, for their trigger analyzer, whatever you want to call it, they've got a trigger programming language. And we're going to learn about some of those programs. Those are all saved with a .ts extension. That's good. I'm not going to even tell you what the special thing you need to remember is until we get there. We're going to go through some analyzer programs. We're going to talk about formatting the display data. Right now, when we do D space TRIMP, we get this big buffer on the screen. And sometimes we'd like to be formatted differently than it dumps it out there. I'll give us an example of that. And there's something probably none of us will ever care about. You can change the voltage sensing, but since I had a scrap of paper that mentioned it, I thought I would throw it in here, get it documented somewhere. In the trigger programming, actually, if we look at that first handout that had some screenshots on it, the second page, page 205, shows some of the things you'll see on the analyzer screen. It shows a state of off, arm, brake, shows commands of reset, init, test, auto arm, and auto test boxes down there. There's something called mode, FIFO, stack, restore, slave. The FIFO and stack are radio buttons, so you can choose one or the other of those two modes. That's what we're talking about here. The state analyzer has enough memory to keep the latest 32,767 records, lines that you executed. And, well, this is not really lines of code because the line of code could take several lines in the display window. But anyway, it keeps that many records. If you're in FIFO mode, first in, first out, it means we just keep shoving stuff into it, and stuff that's more than 32,767 ago gets pushed out the end. We lose them. If we're in stack mode, as soon as we've recorded 32,767 records, we stop recording. Yeah. That's self-explanatory. Everybody knows what that means, right? This trigger programming, we're going to get into some of the program elements now. I brought another book. There's an analyzer programming guide, an analyzer reference that tells us about this language. And I took some of the stuff out of that to make some slides for us. But that's a third book that you can now say that you know what part of it means. Or you will be able to in a few minutes anyway. In this script language, these are saved as files. And looking at Dick's screenshot again, there's an A.P window, a little window on top there. That's where the program is actually entered. So if I'm doing an analyzer program, I'll blow that window up to full screen, full size. I'll maximize it. I will type in what I want. In this write-up he did, he explains that you type that in and then you click on the compile to compile your program. If it shows no errors, then you can go and execute your new analyzer program. But the syntax for writing these instructions, this code, this trigger code, comments begin with a semicolon again. But in this time they can be anywhere in the trigger program. They can be after instructions. They don't have to begin at the beginning of a line. Declarations are addresses, data patterns, or counters. Declarations come at the top of your functions, like the automatic variables that we define in C. Instructions are all the things that we can do. Levels. This is sort of a strange language. We start off in the base level, and we can advance to different levels based on conditionals. We can say go to level 2 if we want to go to level 1. That's going to be a tag in here, and when we promote ourselves to a new level, we'll stay in that level, executing the instructions until we come across something that tells us to go to a different level. One of the weirdest things about the levels is all the instructions at that level get executed at the same time. It goes through all those instructions, evaluates everything, and then if the result of that is that you jump to a different level, you jump. If the result is that you sample and record something to the analyzer, you record it, whatever. So it's sort of tricky at times. You can write a program that doesn't work because you say, if such and such is true, go to level 2. If such and such else is true, go to level 3. And if they're both true, go to level 3 will overwrite the go to level 2. And the result of executing all that is you go to level 3, you never got to level 2, and you won't know why. It doesn't execute the instructions one at a time and do it and you're gone. Also, whenever you're at a level, all the instructions at the base level are getting executed as well. So it's strange stuff, and you can get strange behavior sometimes. If you get to the point where you want to do something really tricky, you'll probably have to read the manual and get better at it. But all the examples I'm going to show are nice, simple examples, so nothing tricky here. The levels begin with a level name followed by a colon. The level name can be anything you want. The easiest names to use are level 1, colon, level 2, colon. You know, we can sort of understand what it's talking about then. There are global instructions. That's what I was just talking about there. they're located between the declarations and the first label. Those are the ones that you start out executing. And they are executed in all levels. The local instructions are valid within one trigger level only. All this will make a lot more sense, or less sense, once we get to real examples. Up in the declaration space, we have address selectors. Address selectors, most commonly, we'll use those to set breakpoints, to define addresses where we want to do something, where it means something special to us. And with the emulators that we have, we've got the RU180 or something unit in there, if you read the different parts that are in there. That one has 3 breakpoints, capable of 3 breakpoints. There's some other ones that have more, but we don't have those. So in the book, when it talks about those other capabilities, we don't have those. We've got 3 breakpoints. Lauterbach has named them for us. They're the alpha breakpoint, beta breakpoint, and the Charlie breakpoint. Do they spell Charlie differently than you do?
Yeah.
It's not named for you.
Yeah.
They had already picked up that name. It wasn't anything special. The abbreviations that we commonly use are AB, BB, and CB, but you can spell those out with bigger names if you want. I'm not gonna. So as an example, you can say ADDR space AB, which is the alpha breakpoint, space CND amount. And that location, that address, which is the 16-bit address plus the page number. So it's the unique address of that location is recorded, and the alpha breakpoint list gets that in there. Another example, we can specify a range of addresses. For the beta breakpoint, we could say CND amount C dash CMD amount C underscore RET. That happens to be one of the functions in ImpDef1. If you needed to refer to all the instructions within that function, you could do something like that. Another thing I didn't include here, you can have multiple addresses, not just a range, but multiple discrete addresses in either one of these, any one of these 3 breakpoints. We could say ADDR, AB, CND amount, comma, CND pan, comma, CND anything else. And I don't think any of us will run into the limit. It's got a limit. It's got limited memory to store all this stuff, but it's a big number. So you can have commas and several lines of tags, and you can make the program way too complex. You can't understand what it's doing. You'll probably screw something else up. So anyway, it allows us to set up 3 sets of addresses. These are the breakpoints that we're talking about, the alpha break, beta break, and Charlie break. The data selectors are also up in the top area. What do we call that top area? Does anybody remember?
Declaration.
The declaration area, that's good. The data selectors provide a name and values. We can do data.b is a data selector. We can give it a name, ASCII, and we can say ASCII is the range. This is the group lowercase a through lowercase z, colon O colon. That means or. And the range capital A through capital Z. So we've set up this data selector name ASCII to be equivalent to this. And when it's in use, we're saying if we get ASCII characters, upper or lowercase, then we'll have a match. Here's how you specify a specific bit. This is for bit 3. This 0 and the exclamation point is how we're saying it's a binary value. Bit 0's a don't care, 1's a don't care, 2's a don't care, bit 3 has to be set. If we wanted bit 3 clear, then we would have put a 0 here. And don't cares for the rest of them as well. And data.b is in this manual that we talked about. We can have event counters. They consist of a name and a data range. Sometimes in a routine, we don't really want to stop the first time we get to that routine, but we have a breakpoint there and it stops, and we go on and it stops again. If we're in any kind of time critical function, we have to type go very quickly, or else we lose our connection or whatever. It'd be better if we could tell it, don't bother to stop till we get to the 10th occurrence. And event counters is how we do that. So just know that it can be done. And if you ever really get to that point, look up event counters in the manual and set something up. It doesn't have to, this one turns true after you counted 10 times. This one is going to be true for 50 through 75 and false before 50 and false after 75. So event counters can be arranged as well. I think we'll actually use these in an example as well. So time counters consist of a name and a data range. They got resolution of 100 nanoseconds. Here's one that's true after 5 milliseconds. So we gave it a, time is the keyword here. This is the name we gave it after 5 milliseconds, and it's 0.5 ms. If you need to wait a certain amount of time before you trigger and start recording. Or if you want to record for only a specific amount of time and then stop recording. Logical operators, we saw the OR a few minutes ago. Here's some more of them. There's exclusive OR and not, and use parentheses for grouping. These are in order of precedence, so if you've got them mixed, the grouping is the highest order of precedence. Yeah, the order it works out isn't right when you've got all these mixed. You throw parentheses in there to specify what you really want. Not is next, and XOR and OR is the lowest precedence. We were talking about those levels earlier. The tags we like to use are level 1 colon, level 2 colon. The level that's active now, that determines the statements that you're going to execute. All conditions are checked simultaneously, like I said. All true instructions are executed. Only one of the levels can be active at a time. And the instructions that can change you from one level to another are the continue, which will drop you down to the next level if it's the last instruction in your. The go to, you can go to level 3, or break to get out of a level. The OS group created a bunch of sample analyzer programs for us. So if you want to use any of those samples that they created, they're all over here. You can look at those. I went through those samples. I used them as reference for creating the next set of slides that we have. They tend to care about things like CTC, INT. Ugh. Those don't make much sense to us, so I tried to use variables and routines that are application-oriented instead of OS-oriented. We're going to look at samples for tracing through the code. Trace means we record instructions that we went through, and then we can go back and look at what we did. We're going to trace selected locations from code, every time we execute this location in code, let's record that. Every time we read a certain variable, let's record that. Every time we write to a certain variable, let's record it. We can trace before halt if you got a program that's halting. We set it up to trace before halt, and that's kind of handy to find out how we got there. Trace before you call a routine, trace to find out how we got there to a routine we didn't ever expect to get to. Trace before write, if a variable is getting changed, we don't know why it got changed, we could set up a trace before write. Trace before a bit changes. We can trace, besides trace before, we can trace after. We can trace after executing a certain location, we can turn the trace on from there. We can trace after reading a certain variable. I want to see, after this is referenced, I want to see what's going on. We can trace what happens after a variable gets written too. When we can set up a trigger event. That's kind of a tricky thing. A trigger event, we could trace after 10 milliseconds. And there's a special script that they provided for us if we're having performance problems, we can analyze the OS overhead, find out how much of our performance problems are because the OS is taking time away from us. If we wanted to trace the execution of selected code, whenever the CND amount routine is started, so we set up this breakpoint, alpha breakpoint on CND amount. We do a sample.enable. That means record this event if alpha breakpoint and opfetch. That means that we're at this location and we're executing code. If we were at this location, if this address came across the data bus because somebody was reading this location, then we don't want to stop. We just want to stop there when we're executing it. Another example I didn't include here, but I often use, is I will set up a range of addresses that's all of the code on a page, and instead of, I will break if we do a write to it. If we write to code space, that's probably not very good. But you don't even have to use an analyzer program for that. This analyzer program says we're going to selectively sample. And that was actually sampling the instruction at that time. If we want to trace the execution of a selected routine, we got a routine that we go through, and every once in a while it takes different logic paths. So let's just record every time we go through that routine, and then we'll go look to see how it went through there. If we do it this way, it does not include subroutines. It does not show the variable data. We can set up an address range. This is that same address range I used in the example earlier. And we sample if on the address bus we've got an address in this range. I could have done an and opfetch there. It would be slightly more correct, but since so seldom do we bother to read our code, this is really the only time we ever get there. But this does not go into the subroutines, which is good for us, but it doesn't show us the variable data. As we're going through, if we load A with a value, we don't know what that value is when we trace it this way. There's another way we can trace the routine that is going to change both of those. It's going to include subroutines and variables. If we don't want to include subroutines, but we do want to include variables, then you got to make it more complicated. But anyway, if we set up 2 of our breakpoints, we set alpha break at CND amount C, the beginning of our routine, beta break at CMD amount C underscore return. I didn't put any global level stuff in here. Level 1 is where we start running Continue if alpha break. That means if it's not alpha break, that's all that we're going to do in level 1. We're going to stick in level 1. As soon as we get to this instruction, to this location, we will continue and drop down into level 2. Level 2 says sample. So we sample the instruction and we stay sampling until this goes true. Go to level 1 if beta break. So once we get to the last instruction, the CND amount C return, then we'll go back up to level 1 and we're not sampling. So we got to our first real program that did sampling that looks like it's doing something useful and we can understand with different levels. Since we're all programmers, we can appreciate that. I'm glad we don't have a non-programming. Let's go back. Remember earlier we talked about the modes. I just call it mode. There was FIFO and stack mode. FIFO keeps recording after we fill up. Stack stops recording as soon as we fill up our memory. If you were recording this, you should use FIFO or stack mode. Trick question.
What do you want to do?
I want to record this
Well, no.
when we're in this function.
Do you want to see how many times you go through it and then stop, or you're just recording to look at the data afterwards? I mean, what do you want to do?
Well, in a function like this, we're probably not going through it very often, and it's not going to make any difference which one we use, because we're not going to get 32,000 samples. So it really doesn't make any difference here. Other times it will make a difference. So in this case, we don't care. We'll probably get to cases where we do care. If we wanted to trace writes to a selected variable like imp buff.
Can I ask a question?
Yes, you want me to go back?
Yeah, if we were in a case where we would fill up all that space and here, then we would want to use stack mode, wouldn't we? So we don't just lose it.
Well,
What happens, we'll fill up the
if
top
we-
and
if
realize
we-
we don't get there.
If we fill up everything, do you want to see the ones you recorded first or the ones you recorded last before you stop to look at it?
Well, it would tell me that we never got there versus
No.
that value drop through and lose
If
it.
you're not sampling anything here. So only when we execute this line do we start filling up 32,000 in memory. So if you never get here, it'll stay at 0. And it actually, as you're recording, it has this window called size that in this example is set to 32,767. But that size will stay there at 0 as you're executing it if you're never getting there. And you can see that size grow as you're recording. If you see it growing very rapidly and you didn't expect it, that's probably a clue that something's going on that you didn't anticipate. Were there any other questions on this?
Yeah, will that only trace the application code, or will you see the OS code in there also?
You'll see the OS code if there's an interrupt.
Yeah.
This
Because you have
one will not record the interrupts because we'll get off in this other address space and we'll go back. Well, I'm on the wrong one. If the address is off in an interrupt routine, that's not going to be inside this function, so it'll go back to level 1, and when we come back out of the interrupt, we'll continue recording. So this particular one will not trace the OS routines. Wait a minute. This one will not trace the OS routines.
Right, because it's subroutine.
Yeah, because this is, the address has to be in this range. This one will trace it because we went off, we invoked an OS function, or we got interrupted and we went off and serviced another process and did thousands of instructions in this other process, and we finally came back and resumed here. So when you're looking through that trace, you can see a whole bunch of stuff in this example that you didn't want to be there. This one, it does include much beyond the subroutines. That's a good point. or it can include them. If we want, did that answer that question? Were there any more? I better go back. I'm not supposed to go ahead till we're ready.
So if you had a process running on a page of memory, you could set this up to just trace anything that happened on that page.
If you want to just one page, you might want to do something like this, where you can give it an address range and sample whenever you're executing code in that address range.
Okay.
The one drawback this has is you don't get to see the values of your variables. Normally, when we trace something, we're very focused, and there's something very specific we want to see. So we don't have those kind of problems. If you crash, and you're just looking to see where all you've been, what was I doing when I crashed, then you start going back, and all of a sudden you find out you're off in another process because it got its time slice, and you got to back through that other process. That's a pain. Yep. Whenever we write to a variable, we can sample that. This is a very simple analyzer program again. Every time a piece of data is changing, you'd sample it. Doing this sample, you'll get to see what the value is that's being written in there. If you got a piece of data that you're wondering, does it ever go off into these weird values that it's not supposed to have, you can write a little program to sample it. You can watch. As you're executing, you can watch this little window to see how many lines you've accumulated. So you can see if it's changing times that you're not expecting it to change. You can then go look at all the values that accumulated. Besides writing, we can do it with a read. Every time this variable is read, if you've got some location, some flag that apparently is getting used somewhere that you didn't anticipate, you can sample on it. This is something interesting. If your program is halting and you want to know how you're getting there, you set up a trace before halt. You do a sample.enable and break if halt.
You mean if the program executes a halt instruction?
Mm-hmm.
What do you mean by halt?
Well, if your program gets lost, it jumps off into data and starts executing data. It might crash, it might halt. And we could set it up to keep sampling your data and break if you halt. If we're doing this, what mode should we be in? Stack mode or FIFO mode? Because stack mode would fill up before we got to the halt, and we wouldn't record the critical event we wanted to see. So this is a very good example of where it's important what mode you're in, as opposed to other times we didn't really care. If you want to see all of the logic that led up to calling a routine, we can specify an address of a routine, we can sample, we can break if we're executing the instruction at that location. This time I put the op fetch on there. Don't have to. Usually it won't make much difference. It's more precise, again, to put the op fetch on there. And which mode are you going to use here? Once again, we have to use the FIFO mode here, obviously, because we want to know what happened when we actually got to that breakpoint. If we fill up before we get there, we're in big trouble again if we're using FIFO, if we're using stack mode. So FIFO is the choice. In fact, anytime we've got a trace before, we probably should be using FIFO mode. Here's trace before a variable is written. You've got a variable that's getting changed. and you didn't anticipate that it was getting changed, or you don't know which place is changing it, so you can trace before it's written. As soon as it's written, you know, you can put a breakpoint on where it gets written, and then you can see where you are. But if you want to see how did you get there, this has recorded all that, and along with the data, the variables.
Stop. Well, excuse me.
Yes?
What is the difference between doing that and simply turning the trace on in general and setting a breakpoint on the variable?
Probably in this case, there's no difference in that I know of anyway. Maybe if we asked an expert, they'd be able to tell us the difference.
But you just said that this records
Oops.
where you've been, and if you just set a breakpoint, you don't necessarily have a history.
Yes, if you have the trace on.
Yeah,
Trace on, and so-
the analyzer is usually on, so we can go over there and it's got a history recorded. Right,
The default is on FIFO, right?
right.
Now,
So we can go over there and look.
This is read, that's right, if it reads it, it would break in your case possible.
No, you can set the
You can break,
right on.
Okay.
yeah. And these little pieces are maybe something you use in a more complex program. So if you want, this is how you do the breakpoint on write. If you want to combine that with something else, you can do that as well. You can put timer elements in there, all sorts of things for your program. In fact, the analyzer is most, oops, I keep pressing the wrong button here. The analyzer is most powerful when you've got a complex series of conditions that have to occur before you actually get to what you want to record. And just the fact that you're executing this code doesn't mean I've done the steps necessary to set it up to where it's meaningful for me. So you can actually have several levels in a fancy program.
Excuse
But
me.
we don't want to get into those anyway.
I don't mean to belabor, but trace before an event, in my mind, can only mean that when it gets to the event, it stops, it's tracing all the time. And when
Well-
it gets to the event, it stops tracing.
That's true. We can turn the analyzer unit off and we can leave the program running. So if you want it to complete the transaction but stop recording,
Right.
then we can use that there.
Oh,
If we're talking to a host and we don't want to lock up that host, whatever. How about instead of before, we do a trace until? Does that sound better? If we're doing a trace until, should we use stack mode or FIFO mode?
Everything's my fault.
Until and before sound like pretty much the same word, don't they? This is a pretty complicated one, isn't it? We're setting up an address. We're defining a set bit pattern and a clear bit pattern. We're sample enable. We deactivate the analyzer trigger unit if we're at this address, TR status, and bit 2 is set. I don't know why I bothered with the bit 4 clear here. We're not using it. Just to see if anybody's paying attention, obviously. This is deactivating the analyzer and stopping the analyzer. The break and trigger.a the trigger unit, this stops the emulator. Well, one of them stops the emulator, the other stops the analyzer. I get confused on this. Really, if you want to stop everything, you got to do both a break and a trigger.a. And you can read about those things, and maybe we'll never have to do it. But this certainly is a much more complex example. Let's see if we got anything trickier. Trace after execution of selected code. Obviously, we can't do this with a standard breakpoint. So this will be a much better example for AT. Soon as we got this in this location, C&D amount, at level 1, we want to continue if we get to that location in code, and that turns on the analyzer. So as soon as we start executing C&D amount, we'll turn on the analyzer and we'll record where we go from there. Do we want to? Which mode do we want to use here? FIFO or stack?
Stack.
Aha, so you're saying we got a different answer finally. Huh?
He used a different quarter.
Mike said that we should always use the FIFO mode. Okay, Jeff says we should use stack. I'd vote for stack too, because I'm interested in seeing what happens from the time we hit this instruction and for the next many instructions. Probably not till we run out of space, but I don't want to lose it when we do run out of space. We can do that trace after, can be after we read some value. It can be after we write some value. You see, these are just continued doing the same sort of thing over and over again. Okay, let's try a trigger event. Let's see if we can understand something trickier. We're going to set up an address at the routine called receipt. We're going to set up a counter that can count up to, that can be false till we get to 2, and then it becomes true. At level 1, we have to do this count enable our count if we're at this address. If we're executing first instruction of this function. So the first time we get there, we increment it from 0 to 1. We continue. If it's true, it's not true yet. So we stay in level 1. The next time we call receipt, it's going to go to 2. It's going to be true, and we're going to drop down and we're going to start sampling. Right now with electronic receipt capture, we call the receipt twice. We call it once to print the receipt. Actually, I guess we call it 3 times. We call it once to preprint, once to postprint, and once to generate the electronic receipt that we capture. So probably should have put a 3 here for the example. But if I want to know what paths we took, what the variables were when we generated that electronic captured receipt, then I'd want to set up an event something like this. I could have recorded receipt all 3 times we went through it, but then I'd have a lot more to wade through.
You said it executed all those lines of code on level 1 at the same time.
Yep.
Would
It evaluates all these, and then it goes and does any actions that you do in there. So the level changes would occur once you've evaluated all of the instructions that have anything to do. And obviously, once we go to level 2, this one doesn't do anything else. We're never going to get out of level 2, so our count's never going to change after that. And according to Jeff, I'll bet we're going to use the stack mode here again. Because he's looking at this word here, after. If we're triggering after an event occurs, we better be using the stack mode. This one we were just looking at. Okay. You've all been wondering, how do we tell what's going on with the OS? How much time is it taking away from us? Dick Malakovich wrote a pretty clever analyzer program that looks to see, are we in interrupt mode, or are we in the CTC stuff, are we in the PTCS code, or are we in something else? And it measures the amount of time that we're spending in all these. It gives us 3 numbers, and it samples for 1 second or something, then we add all those together and we find out what percentage of the time we're actually in those functions. It's called execflag.ts. It's in that sample area that I told you about earlier, in a slide way earlier. This is used, this one works on T7s, this one works on ICE terminals. And it's way too complex an example to throw up on the screen. Besides, by not making a slide of it, I didn't have to read it and understand it. But we can use it. And if you look at the comment in the front of it, it'll tell you exactly how to use it and how to interpret the results. And has anybody come across a case where they care how much time the OS used, where the timing was critical? Not yet, huh? Maybe someday. Actually, when people are complaining about performance, will usually involve someone from the OS group. That this is way too slow, I don't understand it, let's go find somebody who's smarter than I am, and we'll get them to help us figure out why it's so slow. And they might use this. But if you want to, you can go ahead and try it on your own. This is a neat little thing. Okay, here's something kind of neat. Here's 2 things that are very neat. When we display data normally, we have to halt, we have to break in order to get it to update the screen. If that data is in upper memory, you can have it keep refreshing that data up there so you can see it changing as you're executing code. And that works only for data that's in upper memory. If it's in lower memory, this won't work. And instead of display TRIMP, you do an ED colon in front of TRIMP. And that tells it to do it in the live window that keeps updating it. And here's another one. If we want to display formatted data, the step table in MDF1 contains records that are 20 bytes long. If you dump the step table to the screen, you'll see the first one starts here and the next one starts on the next line 4 bytes over because it's formatted 16 wide. So we tell it no orient. That means if step tab starts in at the 3rd location, move that to the 1st location. And this says a width of 20, width space 20. Decimal. If you don't put the decimal in, you'll get 20 hex, 32. I practiced that yesterday, I know. And this is something we don't care about on a day-to-day basis, but every once in a while we're looking at something that is a repeating structure. And it's a real pain because you got to come down and come over. And when they're lined up, so the same field is just straight down the page, you can see, does everything look right?
Or maximum width on that?
I don't know. You want to go try it and come back and tell us? We'll wait.
Is it possible to use a symbol for the width, such as what might be defined in struct.ing?
I believe so. It should be. That should get substituted in there. No, there should be no reason you can't do that. Any other questions or suggestions on this slide? Come on then. This is that one piece of information I mentioned earlier that I was going to stick in here so it's recorded. I was having a problem on Smart Ice when we were doing debug of the application initially. Whenever we tried to print something, the printer was drawing a lot of power, and the voltage bus was sagging so low that the Z80 reset itself. It's designed so that if we lose power, it saves itself. It doesn't keep executing as it runs out and destroy memory or anything. When you get down with the voltage too low, you can be very sensitive. But the Lauterbach emulator also gives you a power fail halt when the voltage dips to a certain level. And that's not necessarily the same plates that the Z80 is going to reset itself. So it's tough to see what the code is doing if the emulator resets itself and the terminal does not. So we can set that threshold. Normally it's set at 4.7 volts about, and we can change that threshold down to 3.3 volts. We may wind up having that threshold change with the new processors they're inventing because they're trying to lower the logic level in these things. And we won't have to know that. When we do that EMU conf, it'll look to see what board type we have, and it will adjust it as necessary. But if you're the lucky one that gets to go fix the EMU conf to add this new board to it, better remember to do this. Anybody, any questions about voltage? Do you know where the term volt comes from and everything? Okay, if you want additional information, you saw I brought my manuals in. I've got 4 manuals in my set, and we actually referred to 3 of them while we were playing here. Now that you've been told the names of the manuals to look at in certain circumstances, maybe they'll become a lot more usable. And the OS group, everyone over there has to understand the analyzer better than we have to. We write simple application code. It usually works. We don't have to worry about debugging it much. They write application code that's doing trickier stuff than we do because they have to do new stuff. They have to talk to the hardware. They have to talk to new hardware that maybe it doesn't work yet. And so the analyzer is much more important to them. It turns out that almost everyone over there is much better at it than we are. And are there any more questions now? Come on, I've been told that we have to record for 2 hours here on this tape. If you don't have any questions, we'll have to show somebody the tape and have them ask questions so we can fill in the end of it. Okay, got a question.
What are the requirements to use source level debugging?
To use source level debugging and have a breakpoint on every source line, you have to have a small program. So we turn that off. To actually use source level debugging, it has capabilities in it that we didn't fully appreciate when we first started to do this sort of thing. And we had to learn how to get around limitations of memory. To do source level debugging with C code, if you get to use the HDT, you may find that you'll load some pages and not include the symbols for those pages. There definitely are limits with Lauterbachs that we have, and we just have to live with those limits. The newest Lauterbachs, the ones from the past year or so, I think, have more memory, don't they, than the really old ones that we have. At some point, there's a difference. And if we have you working on C code and you can't get anything to load or use the emulator, then maybe you'll be lucky you can complain and get a newer emulator. Switch that emulator to some new person coming in. Talking about newer or older emulators, the oldest emulators we have do not have this capability. So this voltage sensing that none of you care about, it's not going to work on the, oops, went too far. Now I'm in trouble. It's not going to work on the emulators either. Let's see, we could just scroll down to the part we want. Can I do it back? I probably can't.
There's your time frame. We're not.
Do the show. Yeah, if I just lean on this button, will we get to the end pretty soon? So we can have our questions? Next time, somebody else has to wear a tie, so I don't have to stand up here and do all the talking. Somebody else can talk. Okay. Those were all fun. Any other questions? Any other thoughts, any suggestions? Is there anything people have done with the Lauterbach that people don't know about that we could share with others here? Or did I catch everything you've ever done? Like I said, did you almost raise your hand?
No.
Like I said earlier, I didn't tell you how to actually run these trigger programs. That's sort of covered in this write-up that has the screenshots on it. Read through there. Probably a little bit of hand-holding the first time or two you do it will be necessary, but we get good at it. It's just like all the other Lauterbach stuff that we do. If somebody holds their hand and teaches us to do something we need to do, we learn it, and then we go on. And there's a few brave souls that actually plowed through all the manuals and learned it that way. But there, yes?
I've had customers ask me for response times from hosts, and you can use the Lauterbach to trace a variable
Yeah.
that you know that your host is going to get, and actually measure the response times.
In fact, when you've got the analyzer screen there, you can set the reference at a certain point and then go down to another point and find out how much time elapsed between those 2 points. And it's usually way too much real estate to have it sampled everything in there, so you'd want to have selective sampling, and you'd use the analyzer to select the points you want. And looking at the times, the elapsed time, setting the reference, there's a bunch of stuff on here that I didn't know how to put any screenshots on here, so it made it easy. Just stuff I could put in slides. Looked like plenty of slides anyway. When to push the reset, the init, the test button, all those things are talked about somewhat in the. If you want to actually execute that file to analyze the OS overhead, you have to read it in, so you type its name over in the analyzer program file, and then you read it in and compile it, execute it. But all those things are doable if we're careful. Okay? Oh well, thanks everybody for coming.